Hello, this is part 2 of Sonic the Hedgehog, the real robot. This is a two-wheel balancing robot, and it's a bit inspired by the Boston Dynamics handle robot, which has got knees that bend so it can lean side to side, and I'm also hoping to put load cells in the legs of this robot so I can make active suspension, and we can try and absorb some of the load from the ground if there's uneven terrain and so on. And this project's a bit of R&D for the openDog project, which is behind me. In the last video on that, I left off putting load cells in the legs and trying to convey the data to the master processor in that dog, and in fact we're going to use CANBus to do that in this project. So this is a bit of R&D, and after that we'll be going back to openDog to hopefully make that work with all 4 legs. This video isn't sponsored, but this is just a quick ad for ways you can support the channel. Of course, I have Patreon and YouTube channel membership where you can get access to all my videos up to a week early, as well as sneak peeks and pictures and the discussion about what's coming up. There's also some affiliate links in the description to this video, and if you use those links I'll get some money, but it won't cost you any more. And those include a free trial sign up for Skillshare, MatterHacker's 3D printing supplies, and also my Amazon affiliate links. In my videos I use music from Epidemic Sound, and there's also an affiliate link for that, which is a really good service for getting music for your YouTube videos. And don't forget my merchandise store where you can get t-shirts, bags, socks and so on of all the things I've built, and I've got the new Performance Robots t-shirts here, as well as openDog, Robot X, the robot arm, and various other pictures of projects. So now it's time to put some electronics in. And that includes 2 oDrive 3.6s, which are the 56 volt version, and these are going to control the brushless motors, of which there are 4, 2 on the wheels and 2 for the leg operation for that suspension. And these basically will control brushless motors and position them very accurately with wheel encoders. The main controller in this project is a Teensy 3.6, which is a 180 MHz 32-bit processor. I've also got an MPU 6050 mounted here, which is the inertial measurement unit that's going to measure the angle. So that's a gyro and accelerometer combined, and it does the calculation to combine all of those sensors on the board. I've also got the NRF24L01, which is the remote control chip there, which is going to communicate with the remote, and there's a little trim pot. And you may notice that these electronics look very similar to the LG balancing robot. And again, I'm going to be using the openDog remote to control the robot because it's already got 2 3-axis joysticks, the other half of the NRF24L01, and various switches and buttons on here so I can control different modes. And this is just an Arduino Mega with lots of analog and digital ins and an LCD with an I2C backpack. So I fitted the main control electronics at the top here, and you'll notice that I've put these on a wedge so that it's roughly level because the IMU needs to be level, and the trim pot there is to trim up the 0 position. It's leaning back a bit here, so the actual balancing point is a bit forward, and that should be just about level, and the rest will trim up in software. The oDrives live in its tummy here. Eventually we'll put a nice blue tummy on with Sonic's white tummy patch. But for now, those are the electronics, mainly to control the brushless motors, so we don't have far to run the serial cables down, and the batteries are going to live just here. And that is a dish around the back there, and that is going to take 2 24-volt LiPos, which are going to be velcroed in, and those are going to be seriesed up to give us 48 volts to power the motors, and so they can run really fast. So I've got my batteries connected to some terminals, and they're wired in series to give 48 volts. Yes, there's a little cover so we don't drop a screwdriver on it and short everything out. So my motor power wires are wired in, as well as the encoder, which is 8192 CPR, which is pretty accurate. We've got that attached to the motor, and the wires run up to the oDrives. So the encoder cables go to my oDrive. I've only got one wired in at the moment. This supports 2 motors. The top one is for the motors and ball screws on its back, so that's the power out to the motors. We've got our brake resistor, and these are the encoder cables. They're a bit long, so I've just coiled them up here. The electronics are still in place up here. I've removed the NRF24L01 and changed it for a long range one with a longer aerial. And I've also removed the trim pot, and I'm going to do that digitally now with the remote. So rudimentary balancing is working. This is exactly the same as the way I did the LG robot. It's going to be pretty quick. It's pretty responsive, so I'm using the openDog remote to control it, and these sticks here will of course drive it backwards and forwards and cause it to turn left and right. So it's pretty responsive and pretty stable. I need to tune it a little bit more, but that's not feeling at all bad. And what we're doing here is of course using a PID controller to go and look at that IMU that we've got, the MPU 6050, and then go and basically control the wheels. It's got a very high integral term, which is the only thing you really need to know about balancing robots. I'm not going to go into too many details right now. You can look at the LG balancing robot series, but I'm going to publish all the CAD and code for this when it's working. So if you want to have a look at my code base, it's actually pretty simple. I've also got some sense of position hold here, which I'm still tuning, which is a switch on my remote. And that should look at whether the robot should be moving, in that whether it is actually having an output and whether the stick is telling it to move and it's taking the difference between those and then offsetting the set point, so it's biasing the angle it should balance at, which is what I do to drive it, and that should hold it in position. It's not working as well as I want right at the moment. It's pretty good though, it doesn't seem to wander off too much. It seems to stick to a spot, and if I push it a little bit, it should come back almost to where it was, but not as much as I want it to. I've also got the trim for the middle position, which is on these buttons. So if I keep pressing the back one, it should eventually wander back. And if I press forward, then it should eventually wander forward. So I can kind of offset it and get it stuck in the middle as well. And then hopefully the position hold should keep it absolutely in one spot. And it now conveniently sits on this stool. So the next thing to do is something about these actuators at the back here which make the legs bend. So what I've done for now is attach those to the steering stick, so as I steer, each of those actuators moves and it bends the legs, so it actually rolls into the turn as it turns round. It struck me it's also possible to use the inertial measurement unit with the side-to-side axis and those two actuators to give it some more stability if it goes over a ramp and one wheel goes off the ground or there's a lump or a bump. Now it'd be logical to go and shorten the leg that goes over the bump, but in fact to stabilise the robot, and this is what's happened in a lot of projects in the past, we actually need to shrink the other leg down and that will kill the oscillation. So I did this with Robot X, and you can see in fact I stabilised front to back and I also stabilised side to side. And it does a thing that a human would do really, which is if someone's pushing you over, you're probably going to bend the other leg and skew your body slightly to try and absorb the load and then return slowly to the middle rather than shrinking the leg that the load is coming from, which means as soon as the person stops pushing you, you fall back and then you sort of would oscillate if you're a robot that couldn't react quickly enough. So that worked quite well. It's also the same mechanism that I used in my BB-8 droids, where the side-to-side pendulum is in fact moving in the direction the droid is moving to push mass back in the other direction, and it's the same as Mark Rober's bowling ball as well to stop the oscillations with that as it was travelling down the bowling alley. So I've got a ramp here, which is only a little ramp, and we're just going to roll over with one wheel and see what happens. And obviously it should be this actuator that shrinks, and that's the one that's going to absorb the load again by bringing it back up when it comes off the ramp. So let's just bring that forward. So we see this one shrink down, but if we push it over, we shouldn't find that we get too many issues because that's nice and dampened in the same way that Robot X is. So we should be able to see that reacting, and that should be killing any oscillations or any wobble that we would otherwise get. So what I've actually done here now is tied that inertial measurement unit axis to those actuators, and it will make the one shorter in the direction that it's leaning, which actually will mean that if there's a ramp, it will tip over even more, which isn't a very good idea. And that's why we need to move on to the next part, which is putting load cells in the legs, which is very experimental to make those act a bit like springs to absorb shocks. So now it's time to put the load cells in the legs. So we've got these load cells, and if you remember, I experimented with these with the openDog series, and I didn't get much further than getting the load from the legs, and I didn't get that data transmitted to the master controller in there. So what we've got now is two teensy 3.2s. Each one's got one of the load cell amp boards on it, which is an I2C device, and unfortunately you can't readdress them. That's why we've got one microcontroller for each one. But also I2C isn't great to run over long distances past all those brushless motors. So that's why we've got the teensy, and we've also got one of the CANBus transceivers on there, which is going to send the data, and that's going to send it over CANBus to the master controller, and this is another teensy 3.6. So now if we have a look in a serial plotter, and I give those a bend, we should be able to see the data there, and that's being received off the teensy, having been sent over CANBus. And I'm doing that about 200 times a second, so we should have plenty of data there, and hopefully we can read those load cells attached to the legs, and then go and move those leg actuators to make the legs act a bit like springs. So I fitted my load cells, they're bolted onto the bottom of the thigh piece with some M4s and M5s, and I pre-drilled the holes in the extrusion before putting this whole thing together. And of course we've got the electronics which is on the inner of each thigh there, and we'll put a cover over that eventually to protect it. So we've got a pair of those, one on each leg, and we've got a cable that takes the signal up to the main electronics, and this is just a twisted pair of cable, and that's all we need for CANBus because it's a differential pair and it's a differential signal. So if noise occurs on this line, it occurs on both lines, and the CANBus looks at the difference between the lines, which should still be the same because the noise has occurred on both of them. And of course I've got another CAN transceiver at the top connected to the CAN pins on the Teensy 3.6. So now if I squash the legs we should be able to see the data that I'm receiving on the Teensy 3.6, so let's give that a go. So there's one of them and there's the other one, and you'll see one is actually much higher than the other relatively for the same amount of force. Oh, I don't know if I squash it, it's not too bad actually. They're not quite scaled the same. Yeah, that one's much easier to squash. So I think that's down to how the load cells are bolted onto the legs. Some of the holes are a bit tight, so it's probably already pre-tensioned the load cell a bit on one of these. So I just need to scale that at the other end I think, and probably make the holes a bit bigger than they need to be if I do this kind of thing again. So now I've tied these with PID controllers to those load cells. So now, as well as balancing of course, if I push it, it acts a bit like a spring, and I have filtered this with a first order filter as well as the PID controller that's saying how it should respond to those load cells. And of course on one side it all responds basically based on the load of each leg, so that seems pretty good. It's not really like a spring because it doesn't keep reverberating, which is quite good because I've managed to dampen that down with the filter of course, so basically it's the sort of response I want really to handle rough terrain. So yeah, I think that looks pretty good. It's a bit like a living being. So I've just got my little ramp here, it's just one bit of wood and some plywood, and we're just going to push that over, and hopefully you should see these react actively as it goes over. So yeah, that did quite a big hop there. Should be able to see both motors basically going crazy there, trying to, don't know how clear you can see that. So I've actually disabled the side-to-side stability using the IMU to drive those actuators and just left it with the load cell stability. And I think that's going to be much better because it is a bit like suspension as opposed to trying to do something clever with the inertial measurement unit. So no matter where the terrain is or where it's leaning, it'll actually still stay upright, and then the load cells will act like springs with suspension that's dampened to absorb any lumps and bumps in the ground or if it goes over little jumps. So I can't really test it in here to give it a proper test, and we've also got the arms to put on and various other cosmetics to make it look more like Sonic the Hedgehog. So next time we're going to do that, and we're going to take it out into a big open area and drive it round and round and demonstrate all the features. There'll probably be some more tuning, so there'll be quite a lot of lessons learnt there. So don't forget to subscribe for more updates on this project and all the other projects, and if you like it then click on like. Also don't forget to check out the links in the description if you want to support the channel. Alright, that's all for now.